Automotive manufacturers put a ton of research and development into air intake design. But when it comes to improving airflow over what comes stock with your vehicle, is that something that can be feasibly done by someone without an engineering background?
Move for me, move for me, move for me, work for me.
What's up, guys? I'm OJ, and you're locked into the FMU YouTube channel, coming at you from Naperville, Illinois, at our automotive facility. Now, you may recognize this E55 wagon from Legit Street Cars. Alex has done his fair share of mods, including a massive 2.9-inch Whipple supercharger, dual fuel pumps, and massive injectors from the boys over at VRP. And then he brought the car to us for some custom exhaust work and a custom dyno tune. Okay, so now here's the humbling part where I've got to beg you guys to like and subscribe, because we're trying to devote more resources in to the videos we're making. Everything's a learning process, and the more eyes we get on our stuff, the more that we can allocate to trying to make our stuff better. So while it might not seem like a big deal going down there and hitting those two buttons, it means a lot to me, so please. Now, as you might remember, this car was giving us some trouble on the dyno before we took the trip to the Indianapolis Speedway. We discovered the intake was causing some unappreciated restrictions the car just didn't like. Now, while that setup might have been good for the stock blower, this 2.9 Whipple and the 90mm throttle body needed a bit more air to run right, which would explain why completely removing the intake brought the power back.
Right there. About 5,000 RPM, it's done. Gosh, what a shame. Other than that, it's clean. We're gonna make a run with no air filters and see if this load limit is actually the air filters cavitating inside. We've seen that, it's possible. After that last run, we're gonna call it a day right there. I don't think it's gonna make any more power unless we make adjustments to the tune, and quite honestly, that is awesome, awesome power on this dyno. So just a little recap, we came in with 428 horsepower with the air filters on a 93, gained a bunch, and then it just kept on going up and up and up to this. So this is awesome.
But we can't just run this open throttle, and the limited firewall spacing makes getting something on there a challenge. Good thing we have a fab shop. Now, we all know that an engine needs air, fuel, and spark in order to create combustion. And assuming you're an automotive enthusiast, you've probably heard the term cold air intake before. Having a free-flowing, dense air supply is vital for engine performance, because the more cold, dense air you can shove into the engine, the more power you're going to make safely. But how do you discern between a well-designed intake from a poorly designed one? How do you know what will work with your car with your mods? Well, we know a thing or two about air intakes. One of our first products was carbon air boxes that we designed for the Audi C5 RS6. These air boxes increase the airflow to the inlets of the turbo to bump up power and sound. We then became known for our early and wide adoption of open velocity stacks calculated to various wavelengths on the E39, E46, E60, and E90 M cars. All of our setups made power and an incredible noise. But we didn't use air screens or filters to protect the engine. This wasn't a good selling point we felt comfortable for the general public, so we didn't sell it. We aren't formally trained engineers, but we do have the want and ability to be able to experiment that we're confident with the designs that they'll meet the demands of our various builds. We need to start at the beginning and determine what our intake is going to need in order to be a proper upgrade. Any factory equipment on the intake has to be accounted for in our design, so determining if this pipe offers any information to the engine computer is where we're going to have to start. This being a manifold pressure reference system means the intake doesn't really provide the ECU with any information. No air mass sensors, no airflow meters on the piping, on the intake means that we virtually have no limitations from equipment to our design. MAP systems are the easiest to design for, provided there are no sensors on the intake track. The only thing present in this application is going to be the crankcase ventilation system inlet, which is easy enough to design for. If this was a MAF-based system, this design would be much more challenging. Now, if you're trying to design this on a mass airflow-based system, the design gets more challenging because of the limitations of the sensor itself. Now, we're no stranger to building systems for mass air meters. And the reason I say why it's a limitation is because the diameter of the piping where the sensor's located, and this is a factory sensor, is very crucial to the engine calculation that it uses to determine how much air is going into the engine. So randomly changing this diameter is going to throw off that calculation. Also, a lot of times, like on this sensor, you have various devices used to straighten out the airflow to reduce the turbulence in order to make sure the reading's correct. On a lot of aftermarket intakes, you can get it pretty close. This is something we chopped off. We have the mount for where the sensor goes, and as you can see, there's no fins or air straighteners inside of there, and it does a pretty good job of calculating the airflow. So depending on the car, you might have a little bit of leeway in order to do something like this if you're upgrading. But again, diameter is very, very important. That is, if you don't want to have to change the engine computer program in order to get it to run right. This is a system we did on a Audi RS6, the C5 way back in the day. Again, this is the airflow meter, air mass meter sensor. The tubing diameter, how straight we have this was very crucial in order to get this thing to run correctly and run right. And I can't stress the importance enough of how crucial the diameter around the air mass meter is to the calculation of the car. Manufacturers who develop these intakes often go through lots of R&D in order to get the car to not only make more power, but to keep that calculation correct. Some companies might step the sizing up behind the air mass meter. They might step the sizing up before the air mass meter. And while that can work, that could also have some unintended turbulence if the sizing's wrong. And the way they figure this out is through either airflow testing or a good old dyno like we do here. Now, when it comes to materials, constructing your air intake can go a lot of different ways. Now, we're a fab shop. It goes without saying we're probably going to use metal. But even then, there's a few choices when it comes to metal. Steel works fine. However, the corrosion and moisture that's involved with taking air in and out lends itself to breakdown of the piping. Over time, it's just not desirable. It's not going to look very good, and it probably won't last too long. Stainless steel, we work with it all the time, but there's a reason why we don't choose that for intakes. And a big part of that is weight, as well as its conductivity of heat. It tends to absorb heat a little bit better, which means it's going to radiate heat for longer. And once it gets hot, it's going to really cook that air and take a long time to cool back down. Aluminum's got some interesting properties, which it's easy to work with. Comes in a variety of different sizes if you're trying to piece something together yourself. And its heat conductivity, where it will radiate heat away a little bit quicker, can be beneficial in certain applications. However, that's works both ways sort of thing, because yes, it can radiate heat away quicker, but it also absorbs heat quicker, which can be a downside to your build. So even with that said, aluminum's pretty easy to work with. We're gonna go with it, and that's what's gonna allow us to try to come up with a design that's going to protect the car using filters, but also allow us to feed the air to the engine that it needs. So there's multiple ways to skin a cat, right? And we've got another car here with an aftermarket blower, this one being from WiseTech. Similar blower setup, even the location of where the blower terminates on the backside, the inlet for it, is similar, but as you can see, they're doing a little something different here. with the duct that goes into the blower inlet. So putting the throttle over on this side, and it looks to be that this thing had some sort of throttle body upgrade on top of the Wistek, because I don't think this many welds is part of the package. But that being said, you can see how this design incorporates a tracked for the intake direction, which cuts over here into the fender well. It's got a nice little plate to block off some of the engine air, and a little bit of the gold foil on there to further maybe decrease some of the engine temperatures. What we're dealing with is this section back here going to the firewall. Now, it not being our kit, for us to redesign the wheel, we would have to make a similar inlet to get to one side for it to be feasible, or some sort of goofy piping that tries to make the maximum amount of diameter turn before, so we can get down one side. You know, we're dealing with such a tight space from the inlet to the throttle body to the firewall that, you know, it's just gonna be a little bit more feasible for us to do a dual setup. Now, you would think the next thing we need to do is find out exactly how much airflow is going to be optimal for this setup. Yes and no. Bear with me. Now, I can derail this thing right here with calculations and equations, but I'd like to keep this practical. I'm not an engineer, not even a little bit. I'm just a mechanic, but I'm here hopefully to convince you that you don't need to be an engineer to make noticeable improvements to your vehicle, as long as you have good automotive common sense and or you're good at Google. For the sake of explanation, I'm going to run you through the math equation for figuring out the optimal intake duct size on a bone stock E55 AMG. We're not going to get into the nitty-gritty of the full explanation behind how we arrived at every variable of this equation or where the numbers came from. There are plenty other videos for that, and it will make ours boring. For once we get all of the answers, you'll see why figuring this out doesn't really matter in a practical, we're building it ourselves application. This is the formula. Now, D1 is the diameter of the intake pipe, VE is the volumetric efficiency of the engine, and in our case, assuming around 118% for the M113. The displacement is 332 cubic inches, and the RPM peak is 6,500 at the top of first gear, which in this case is 51 miles an hour, which is the low end for the RPM that you would be seeing to not assist with ram air. If we plug all those numbers into, this is what it looks like. D1 equals the square root of 118% times 332 times 65 times 144 times 41 over 51, 88 times the calculation 3.14. Run this all through and we get 5.49 inches as the optimal side for a single air pipe. But we're gonna need 2 for the optimal size of the pipes, as this car came with dual intakes. This isn't a clear cut, the diameter in half deal. This relates to the total area. Now, the answer of D1 in this formula, D2 equals the square root of D1 times 0.05. Plug in D1 and solve. Okay, so this gives us 3.88 inches of diameter that we need for the 2 intake pipes on a bone stock M113K. And this is weird because the factory intake is way smaller than that, isn't it? It doesn't mean Mercedes themselves designed this optimal intake wrong, did it? Yes. Their focus is working within the space constraints, optimizing low-speed drivability, enhancing fuel efficiency, reducing emissions, and minimizing engine noise, rather than prioritizing uncompromising maximum performance. Okay, so what if we are only worried about power? Well, this engine's been modified to produce well over 300 horsepower more than the factory car, which means technically speaking, we would have to rerun our equation to consider the extra power, since it will need a lot more airflow. Why aren't we doing that? Because we can't fit the intake that size regardless. Realistically, at best, we can only fit 3.5-inch pipe on each side. Plus, on top of that, this Hellcat throttle body is 92 millimeters or 3.62 inches, which you'll notice is substantially smaller than the D1 number of 5.49. So that's immediately a choke point. So I've been talking about this from the beginning, that sometimes what's optimal, what's best for the car's performance, doesn't necessarily mean it's gonna fit. You hear me say this a lot with our exhausts as well, where I say we're dealing with space constraints. This is hot rodding stuff. This is performance on what you're working with. It's not like we're building a tube frame car and we can make whatever design we want for the intake because we're starting from square one. We have to work within the confines of the vehicle, and some things need to be sacrificed. So on the factory intake, it's durable plastic that insulates from heat pretty well. It fits to where the car needs to, and it flows enough air for the factory setup. It also does a great job at keeping the car very quiet so that it still retains its Mercedes-like mannerisms. However, this isn't that anymore. We're adding almost 300 horsepower to what the car wanted when it was originally designed. We've got a small space to supply that air. So the idea here is, what can we do with this space back here in order to maximize the amount of air that we can get in through this 92 millimeter throttle body? But there's other things that we have to take into account. Going to one side and leaving that piping, let's just say we went, 3.5 inch all the way down, 3.6. We would then have one intake, which, as you know, wouldn't be enough according to our calculation. But again, if we merge it to two, that becomes the choke point. See, piping is all about not only its size diameter, but also the length. You're going to have a pressure drop the longer the pipe gets, the ability to flow air, and you'd like to minimize that, but again, back to the beginning, we also need filtering in there. And the filtering is keeping the engine safe from outside particles, debris that could potentially hurt the car. We need to do all of these things in this space, and the best way to go about that, I think, is using two 3.5 inch pipes that have to come up to some sort of configuration up here to get back onto that 3.6 diameter throttle body. Now, we've come up with a few ideas, a manifold of sorts, a box, but another problem with our shop doing this sort of thing is the repeatability of it. Let's just say a few of you end up liking the design of our intake and you want to get one for yourself. Well, if I've got a manifold with 50 different bends that we put together, that we fab up, and it's extremely difficult to reproduce, it doesn't really help us out in the future. So simple's king here. We want it to be simple, we want it to be effective. We've got to kind of come up with a design, which is why I'm gonna lean to one of our friends. I believe he was in one of Alex's video, but Oliver is gonna help us 3D design for printing a manifold that might work on this. So while we tried originally making a design that incorporated kind of a boxy manifold, the angles that we needed to get in order to get to a 3.6 inch back out to 3.5, moving it around, maximizing the area, maximizing what we could fit in there, ended up being very complicated. So we reached out to Oliver, who had been apprenticing here at the shop over the summer, and he offered to help us out with a little bit of CAD design and 3D printing, something that he does as a hobby, and was able to come up with a design that was a lot simpler than what we were doing. Here's what we got here. We have a 4-inch section here, which allows us to clamp onto the throttle body, going into the 3.5s. Now this was kind of beautifully simple, but it needed a few renditions, a few prints to get just right. While there's lots of thermoplastics we could use to use an actual piece that's 3D printed, this is simple enough that we could make in-house out of aluminum. So that's what we'll be doing. And here's what we came up with. As you can see, it's pretty much a replica, except out of aluminum, of the piece that Oliver went ahead and created. I'm gonna get this on here, and then we're gonna go over the ducting and the filters and how we're gonna finish the rest of this system. All right, so here's what we're working with. Here's what we're thinking. There's a lot of ways we could have gone with the filter setup, panels, boxes. I really wanted to use some sort of canister filter. However, in order to flow the proper amount of volume, and that's a real hard figure to try to find, we needed something pretty big on the body. The stuff that we were working with, the BMC carbon dynamic airboxes, the stuff we had used in the past on these supercharged motors such as the 32 AMGs, just weren't fitting in this space when you close the hood. We came across these Volant power core filters, and judging by all of the information I could find, they looked like they'd flow enough air that it wouldn't be too much of a restriction for this vehicle. Ultimately, the dyno is going to tell us if we nailed it or not, but as you can see, we've got pretty much the design laid out. We're going to finish that up here, get everything into place, and then go see if we can make numbers that are close to how the system ran without any filters. Now I've got a size comparison of the old system here, and as you can see, we stepped up quite a bit in the diameter of this piping, and as we were saying at the beginning of the video, a bigger diameter isn't an equal size up when you're stepping up in sizing as far as flow is concerned. It's more the cross-sectional area that allows more air in, so even though this is only a ½ inch bigger, it actually is going to flow a lot more air. So here we are, the moment of truth. We need to see if what we came up with is going to actually work and get us near that number where we had removed the air filters. And if we do, and we have a filtered setup, I'm going to call that a success. So a few things to remember before I get into our conclusion. When Alex had his peak numbers that he ended up showing in his video, he was running E55. Now, what we're looking for is a setup that gets us close to running without the air filters. Now, E55s are notoriously hard to dyno because in order to get the max number, you probably have to let it cool down for about 20 minutes run after run. We're seeing numbers that are within spitting distance of where we were at with the no filter setup, and I think if we let it cool down, we'd have proper numbers. So as you can see here, I've got 3 numbers. 483 was our no filter number when Alex ran it with us before, 465 being the number that we just hit on a hot engine doing multiple runs, and 428 is where we had the cut. As you can see, that hard line is where the car would cut before. So we're no longer cutting, but we do have a little bit of power difference. However, I'm going to chalk that up to it being heat and us not allowing proper time. But for the sake of the video and trying to get this thing out to you, we're going to wait till next week when we do the proper dyno tuning on this car, as well as finish up the intake with a little bit of cosmetic upgrades. So what did we learn here today? Well, the big takeaway is your biggest issue you're going to be fighting when designing an intake is always going to be the space constraints. So maximizing the amount of air that goes in there without disturbing any sensors is always the best way to go. But testing is really the only way you're going to be sure that what you did had any effect. Well, that's it for this week. If you guys have any questions, make sure to drop them in the comments below, and stay tuned for next week when we get this thing and try to see what it'll do with a proper dyno tune. See you then.
For me.